Forging ahead, let's proceed to the second method, which is applicable in cases where an exponential expression equates with a constant that cannot be expressed as the power of the base of the exponential expression. So let's take a look at some example. Find x if 8 raised to x is equal to 17. So we know, class, that 17 cannot be expressed as the power of 8, especially 17 is a prime number. So in this case, we have to use the laws of logarithm. So by taking the logarithm of the both sides, we will have the logarithm of 8 raised to x is equal to the logarithm of 17. Then, if you can see, it is familiar because in here we can apply the law of logarithm of a power, so resulting to x times the logarithm of 8 is equal to the logarithm of 17. To get the value of x, we can simply divide both sides of the equation by logarithm of 8, giving us logarithm of 17 all over the logarithm of 8, which is the element of our solution set. Next example. What is x in 10 raised to 5 minus x is equal to 14? So just like the previous example, it cannot be expressed, 14 specifically cannot be expressed as the power of 10. So we have to take the logarithm of the both sides. The logarithm of 10 raised to 5 minus x is equal to the logarithm of 14. And we can also apply to the left side of the equation the law of logarithm of a power, giving us 5 minus x times the logarithm of 10 is equal to the logarithm of 14. Now, notice, class, that we are using here a common logarithm. That's why its base is equal to 10. And we know that one of the laws or properties of logarithm is that whenever the base and the power is the same, it is just equal to 1. That's why we will have 5 minus x times 1 is equal to the logarithm of 14. Simplifying it, we'll have 5 minus x is equal to the logarithm of 14. Adding negative 5 to both sides of the equation, we will have negative x times the logarithm of 14 minus 5. Then multiplying both sides of the equation by negative 1, we will have x times, or x is equal to 5 minus logarithm of 14, which is our solution set. For our last example, for method 2, we have to find x in e raised to x plus 4 minus 7 is equal to 8. So as we can see, there's a constant in the left side of the equation. That's why first we have to combine similar terms. Adding 7 to both sides of the equation will yield to e raised to x plus 4 is equal to 15. Since we are dealing with the Euler's constant e, instead of using logarithms, we can use the natural logarithm for our calculations to be easier. So taking the natural logarithm of both sides, we have the natural logarithm of e raised to x plus 4 is equal to the natural logarithm of 15. And we know, class, that if we apply the inverse property of natural logarithm in the left side of the equation, we will have x plus 4 is equal to the logarithm of 15. Simplifying it by adding negative 4 to both sides of the equation, we will have x is equal to the natural logarithm of 15 minus 4. That is the element of our solution set. Let's proceed to the third method, which is applicable in cases where an exponential expression equates with another exponential expression that cannot be written as the power of the same base. So it is just the same as the second method for the second cases. However, instead of dealing with a constant, we are dealing with an exponential expression. For example, What is x in 7 raised to x is equal to 25 raised to x. So again, we have to take the logarithm of both sides. We have logarithm of 7 raised to x is equal to the logarithm of 25 raised to x. Then applying the law of logarithm of a power, we have x times the logarithm of 7 is equal to x times the logarithm of 25. Then we can combine similar terms by moving this or transposing this to the other side of the equation, giving us x times the logarithm of 7 minus x times the logarithm of 25 is equal to 0. We can further apply distributive property, so we can distribute x, giving us x times the difference of logarithm of 7 and logarithm of 25. So to solve for the value of x, we need to divide both sides of the equation by logarithm of 7 minus logarithm of 25. And we know that 0 divided by any value or any number is just equal to 0. That's why our solution set is the set containing 0. For our second example, we have to solve for x in 3 raised to x plus 2 is equal to 5x. So just like the first cases in our, or just like the first examples in our method 1 or method 3, we have to take the logarithm of both sides. We have logarithm of 3 raised to x plus 2 is equal to the logarithm of 5 raised to x. Then we can apply the law of logarithm of a power, giving us x plus 2 times the logarithm of 3 is equal to x times the logarithm of 5. So we know, class, that our goal is for us to place all the expressions or the terms that have the variable x in one side of the equation so we can um, easily find the value of x. In order to do that, we need to first distribute this into this. So we will have x times the logarithm of 3 plus 2 times the logarithm of 3 is equal to, just copy this, x times the logarithm of 5. Next step, we can now combine terms with the variable x. So we have x times logarithm of 3 minus x times logarithm of 5 is equal to, moving this on the other side of the equation, negative 2 times logarithm of 3. So we can multiply both sides by negative 1 to give us x times logarithm of 5 minus x times logarithm of 3 is equal to 2 times logarithm of 3. Then we can distribute x. We have x times logarithm of 5 minus logarithm of 3 is equal to 2 times logarithm of 3. We can further divide both sides of the equation by this term, giving us x is equal to 2 times logarithm of 3 all over logarithm of 5 minus logarithm of 3, which is the element of our solution set. For our last example, for method 3, we have to determine the value of x in e raised to 2x minus 6 raised to x plus 1 is equal to 0. So we can move or transpose this to other side of the equation, giving us e raised to 2x is equal to 6 raised to x plus 1. Then, since we are dealing with exponential equations with the Euler's constant e, we can use natural logarithm instead of logarithm to make our calculations easier, as what I've said earlier. So taking the natural logarithm of both sides will give us the natural logarithm of e raised to x is equal to the natural logarithm of 6 raised to x plus 1. So by applying the inverse property of natural logarithms, we have 2x is equal to natural logarithm of 6 raised to x plus 1. Then we can also apply on the right side of the equation the law of logarithm of a power, giving us 2x is equal to x plus 1 times the logarithm or the natural logarithm of 6. Then we can perform distributive property on the right side of the equation to give us x times the natural logarithm of 6 plus the natural logarithm of 6 because this is just 1 times the natural logarithm of 6. Then, combine similar terms with the variable x, giving us 2x minus x times the natural logarithm of 6 is equal to the natural logarithm of 6. Distributive property is applied to obtain x times 2 minus natural logarithm of 6 is equal to the natural logarithm of 6. Then we can divide both sides of the equation by this, giving us x is equal to the natural logarithm of 6 all over 2 minus the natural logarithm of 6. And finally, we have our solution set containing the element the natural logarithm of 6 all over 2 minus the natural logarithm of 6.